Hi everybody, so today I want to tell you about a few steps we took towards designing scalable threshold crypto systems. This is joint work with my high school students who I've had the pleasure of mentoring for the past 2 years, my collaborators at VMware Research and my advisor. Let's begin by talking about signature schemes. In a signature scheme, you have a device who has a secret key and can produce signatures on a message, and a verifier who has the corresponding public key can verify the signatures on any message M. The problem here is that if the device is compromised, the adversary can get its hands on the secret key and forge signature on any message it pleases. Signature schemes are used a lot in applications like secure web browsing or secure messaging such as WhatsApp. So it's really problematic if in that setting the adversary gets the secret key, because it can impersonate your friends on WhatsApp, or it can steal your Facebook password, or so on. One way to address this is to use a threshold signature scheme. And the idea here is that you split the secret key amongst multiple devices, say 5, such that only 3 or more devices can actually produce the signature and no less than that can. So for example, here device 1 produces a signature share on the message M using its share of the secret key. Device 3 does the same, device 5 does the same, and then they send their signature shares to an aggregator who produces the final threshold signature under the secret key SK, which none of the 5 devices knows. And then the verifier can take this signature sigma, this aggregated signature, and verify it under the public key corresponding to the secret key. And in fact, the verifier can be completely oblivious that this is a threshold signature scheme. And the nice thing is that if you do this T out of N sharing, where you need T players to construct a signature, you can tolerate up to T-1 compromises. So it gives you a lot of resiliency. And this is useful for a lot of applications. Things like cryptocurrency wallet, where you protect your Bitcoin key by splitting it amongst trusted parties. Consensus protocols, where you can get scalability. Random beacons, where you can get randomness. Voting, although this would be a really naive voting that doesn't preserve privacy. And for the voting use case, you actually need large thresholds and large numbers of players. And I think more applications are likely to come if you think about this decentralized future that some of us are hoping for. And in this talk, we want to prepare for this future by scaling threshold schemes to really large thresholds T. And I say threshold signature schemes, but actually our techniques will apply to any threshold crypto system. And as a bonus, because this future might be really far away or might never come, who knows, we also want to get efficiency at small scales too. So let's see what are the challenges here. One challenge is, how do you do the splitting of the secret key? The first answer is to use a well-known line of work called Verifiable Secret Sharing. And this allows a dealer who knows the secret key to split it in a verifiable manner. Unfortunately, the dealer knows the secret key, so that means the dealer can sign, and that means you no longer have a threshold scheme. So to address that, you can use what's called a distributed key generation protocol, also a previous line of work, where the 5 phones in this example generate the secret key jointly, but without actually learning it. The only thing the 5 phones learn are their share of the secret key. So it's quite magical, but it works. And in fact, the key ingredient in the DKG protocol is n parallel executions of a VSS protocol. So for the purpose of this talk, we'll just be talking about verifiable secret sharing and scaling it rather than DKG, since DKG scaling follows naturally from that. The other difficulty is, how do you aggregate that scale? And the problem here is that you need to use Lagrange polynomial interpolation, since all of the verifiable secret sharing schemes are based on polynomials, well, all efficient ones, I should say, to be more precise. And Lagrange interpolation is a bit slow, and we'll fix that too. And let's start by talking about VSS protocols. And we'll begin with a non-verifiable secret sharing protocol by Shamir. This is a classic technique where you take your secret SK and you pick a random degree T-1 polynomial, phi, such that phi of 0 is equal to the SK. And then you send each of the n players, in this case n is equal to 5, a share of their secret key by giving them phi of I. Each player I gets phi of I, and that's their share of the secret key. And now for the reconstruction, each player, you have a subset of T players, and they send their share to a reconstructor, and the reconstructor can use Lagrange interpolation to actually recover the secret key Sk by interpolating phi of 0 from these evaluations of phi at 1, 2, and 5. And in fact, it doesn't matter what subset you use, any subset you use will always lead to the correct secret key Sk. However, the assumption here is that the dealer behaves correctly and gives players their correct shares, and also that the players behave correctly and give the reconstructor the correct shares. But that's not always the case, so we have to handle attacks somehow. And a previous line of work on verifiable secret sharing does exactly that. And the idea is as follows. As before, you do your Shamir secret sharing using a polynomial phi, but this time you will commit to phi using a polynomial commitment scheme. And you get this commitment C, and as the dealer, you broadcast this commitment to all of the players. And you also give each player a proof pi I that their share phi of I is correct. And the player can verify this with respect to the commitment C. And some of you might notice that you might be able to break this by giving different players different commitments. But again, I said broadcast channel. So the dealer broadcasts C to all of the players, and the broadcast channel ensures that all players agree on the commitment C. So that prevents the dealer from giving different players different shares of different polynomials phi. And now during reconstruction, we had the problem that some players might give bad shares, but now the reconstructor can ask for proofs and can easily detect if a share is invalid and safely ignore it. And the reconstructor is also assumed to have the commitment C from the broadcast channel. Okay, so one scalability challenge here is that these polynomial commitments are either big or slow. In particular, if you look at something like a Peterson commitment, this is order T sized, so it's a bit big in the threshold T. However, if you look at other schemes like Kata-Zavirucha-Goldberg or KZG commitment, the commitment is very small, it's constant, but the time to compute proofs is now n times t. And since the threshold t can be n over 2, this can be really problematic for a lot of applications. And let's see what a KZG commitment looks like. It just looks like g raised to the evaluation of phi at a secret point tau that nobody knows. And there's a question here about how you actually compute this without knowing tau, but there's a way of doing it as long as you also have a commitment to tau in a certain form. So we won't go into details about that, but it's a beautiful scheme. And we actually, in this work, we focus on reducing this order NT time for computing all of the proofs. Because, let me show you how this affects VSS dealing. So suppose you implemented VSS using KZG. On the y-axis, you would have the dealing time. On the x-axis, you have the number of players n, and the threshold t would be set to n over 2. And the dealing time scales quadratically with the number of players. So for example, at small thresholds, you get reasonable performance. As the threshold increases, the performance decreases very fast. And if you're talking about really large thresholds, then the performance is outside the realm of practicality. Now, in contrast, with our new technique for pre-computing KZG proofs fast, we drastically reduce the VSS dealing time. So we get orders of magnitude improvements at really large scales. And these improvements are still significant as the scale decreases. And they're maintained even at small scales. So we get almost a 10-fold improvement for 2,000 players. And the key ingredient here is something called a polynomial multipoint evaluation. So what we're going to do is, suppose I have my polynomial phi and I commit to it, and now I want to compute proofs at points 1, 2, 3, and 4. I will define this accumulator polynomial over 1, 2, 3, and 4, and I will divide phi by it, and I'm going to get a quotient and a remainder. And now I'll repeat this process recursively with this remainder and with the left half and the right half of the accumulator. So I'll divide the remainder by the left and by the right half, and I'll get some new quotients and some new remainder. And then I do the same here and here. And I divide the remainders by the left and right halves, and I get some quotients and some remainders. And in fact, in the leaves of this tree, the remainders will actually be the evaluations of phi at the points in the root. So just take my word for it or read the paper if you want more detail. It turns out the time to do this polynomial multipoint evaluation is order n log t. Actually, that's only true when these points are roots of unity, and I'm ignoring that in the slide. And now let's see, so far I'm just talking about how to evaluate the polynomial. I'm not talking about how to actually get proofs for those evaluations. And here's how we get the proofs. Let's ignore the divisions happening and just focus on the quotient and the remainders. And let's also ignore the remainders and just focus on the quotients. And the idea is that I'm going to commit the quotients using the KZG polynomial commitment scheme. And I'll get something that we call an authenticated multipoint evaluation tree, or an AMT. And the idea is that this AMT can be computed in n log t time. So I do the multipoint evaluation and then I do the commitment, also in n log t time. And now a proof for the evaluation of, say, phi of 3 is just the path of the quotient commitments leading to phi of 3 in the tree. And the size of this proof is order log t. So now I'm trading off the proof size because a KZG proof was order 1. I didn't mention this before, but it's actually very small. Our proof sizes are bigger, but it takes us much smaller time to compute them. So we're trading off proof size for computation time here. Again, to compute n KZG proofs, I would have spent order nt time, but now I'm spending order n log t time, and I'm getting log t sized proof rather than constant sized proofs. And okay. So the road so far was, we were talking about how to split the secret key efficiently, and for that we had to scale these verifiable secret sharing protocols by figuring out a new way to compute proofs in KZG polynomial commitments. And I claim that this also leads to a scalable distributed key generation protocol, and you can see the details in our paper. Now, the next question is, how can we aggregate threshold signatures at scale? And the answer here is you can use Lagrange interpolation, which is a bit slow. And let's see why that's the case. Well, before we see why that's the case, let's see exactly how slow it is. So on the y-axis, I have the time in seconds, and on the x-axis, I have the number of signers, and the threshold t is set to n over 2. And as you can see, the aggregation time scales quadratically in t, so it doesn't scale very well. You get good performance at small scales, but it decreases very fast, and at large scales, the performance is impractical. So why is this the case? The reason we don't scale well is because to aggregate a signature from a set of t players with IDs in the set P, we have to compute all of these t Lagrange coefficients. Now let's see what they look like. They look like this, a numerator divided by a denominator. The numerator you can actually compute it in order t time, because you can compute this product once in order t time, and then you can go do this division t times, and you get all of the t numerators for all of the LIs. But the denominator, unfortunately, if you do it naively, will take you order t squared time. And it turns out that you can do it much faster using a polynomial multipoint evaluation. And I won't go into details about that, but the idea is that you take a derivative of a certain polynomial. In fact, you take the derivative of the accumulator polynomial that I mentioned before, and you evaluate that derivative at all of the points in P. And then you get all of the denominators. And so you can check out our paper for more details on that. And now the performance boost you get for that is significant. The polynomial multipoint evaluation takes you t log squared t time. So you reduce the aggregation time from tens of hours to tens of seconds, from a few minutes to a few seconds. And at small scales, you get like a 2x maybe improvement. So we're very happy with this, and we hope future applications can benefit from this. But also I think some applications might benefit even today. So there are, for example, consensus protocols that need quorums of size a few thousand, such as Definity, I believe. And those protocols can benefit from these faster threshold signatures. All right, so to conclude, we showed how to aggregate threshold signature using faster interpolation algorithms. So order t squared time versus t log squared t time. And in particular, this applies to other threshold crypto systems like threshold encryption schemes, not just threshold signatures. So really, this is applicable to any crypto system that does interpolation in a finite field of prime order that has support for roots of unity. And then we showed how to scale VSS and also, as a result, DKG protocol by computing proofs in KZG polynomials much faster using this AMT technique. So we improved the time from order nt to order n log t. But we did increase the proof sizes from order 1 to order log t. And in general, any technique for computing KZG proofs faster is very useful because you can use it for things like vector commitments and who knows what else. Perhaps authenticated data structures based on polynomial commitments, which are very popular nowadays. And I think there's actually some exciting new work in this direction by Feist and Kovratovic on how to compute all KZG proofs in n log n time, and the proofs are constant sized. So asymptotically, you do better than AMT. We've implemented this, and although the computation time is a bit higher, the proof size is smaller. So we're very excited about seeing how this applies to VSS and DKG protocols. And you might say 1 million is unreasonably large. What are the applications for that? But again, that's for the future to decide, and we are faster at small scales too. And as future work, we need to address the overhead of complaint broadcasting in VSS and DKG protocols. And we need to scale the broadcast channel, which needs to send these commitments to millions of players. And I'll leave you with a link to our repository. And I'm ready for questions. Thank you so much.